And it's a very fluid set of slides, which means that you have welcome to stop and ask questions if it's not clear. And I haven't even finished preparing slides for tomorrow, so it's going to be based on what your feedback on today. So whatever you want to hear. So, but first, so I'm going to use the board a lot to elaborate on some of the arguments and show some calculations, because I think sometimes calculations are useful. But first, I'm going to start with some motivation about what am I doing. So one of the key results of Shannon was the fact that when you have a memoryless channel and you want to communicate over a channel, he gave an expression for capacity as the maximum mutual information. I'm assuming here that people have seen these terms. So if you haven't seen, please ask me, but I hope you have seen. But so this is a well-known result. And also, if you look at the capacity, another way of writing the capacity is to write as a set sequence of achievable rates, and you normalize rates, and you can see this is achievable. And if you take independent copies, you see that this is at least as big as this. So you can say one of the main contributions of Shannon was one of the things that made this very appealing was that you didn't have to do this asymptotic calculation, but you could do a single letter calculation. So this is the single letter thing that people. Can you briefly remind us the mutual information that h of x plus h of y minus? Yes. So IXY. Yes. So IXY is just entropy of x. There are many ways to write this. Entropy of y minus entropy of xy. It's also equal to entropy of x minus entropy of x given y. It's also equal to entropy of y. It's symmetric. Entropy of y given x, and it's also equal to the divergence between the joint law and the product marginals. So you can view it in any way, any of the ways you want. So x to the n means a sequence x1. So superscripts denotes a sequence xn. And so you can think of a joint. So, and a memoryless channel means that the law w of yn given xn, if there's no feedback, it essentially becomes product over I, the same channel of yi given xi. That means it's just, so the output at time I depends only on the input at time I. So that's the setting where I am. And under this setting, we can see that this maximizer is exactly equal to this. So you don't gain anything by going to multiple letters. This is what made the whole field interesting. Because if we had to compute this asymptotically, then it's much harder to do. This is it's a finite dimensional problem, so it's much easier to compute this. This made it interesting. Okay, so this is kind of the motivation, and what is the reason for this? So I'm going to quickly say, because this is really the motivation for the talk. Why does this hold? So all I need to show is that if I double it, it doesn't improve. So let's see what happens. Why doesn't it improve when I double it? So I'm going to write the mutual information of a doubled alphabet as the entropy minus the conditional entropy. Now, okay, here I'm going to maintain this term, but what about this term? Because channels are independent, so you have clearly that y1 to x1 to x2 to y2 is a Markov chain. So this just breaks up as the sum. This is an equality because the independence, conditional independence, and then I use subadditivity entropy to write this, and that gives me this. Therefore, the maximum of this is less than twice the maximum of this, and so essentially the key thing is the subadditivity entropy. So that's what helps us get from the n letter to one letter. Okay, so that's really the reason why you have a single letter expression. And I'm going to use two words. Subadditivity and tensorization, they are basically the same phenomenon, just viewed in a different light. So sometimes I speak subadditivity, sometimes I call tensorization. And why am I calling tensorization? Because I'm really taking independent, channels have just tensor products. So, and they also, and this is the word that sometimes used by analysts and so on, but they're same. Okay, question?
What would be the simplest
What would not hold?
I mean, this sigma.
Oh, for any fixed channel, this holds, but if I change the channel over time, it will not hold, right? So this doesn't depend on the channel. It could be W1, W2, as long as independent, the whole proof goes through. Right? So this is always true for any channel, any discrete channel. That's
why you don't write lim sup? If you say that for any fixed m, this doesn't increase.
Oh, the point is that any maximum, there's no, I just wrote lim sup because you could do it for any n in capacity is asymptotically, so you can achieve lim sup if you wanted to. But it's a limit actually because it's super additive, so it's a limit. And so there's no lim sup. You can replace lim sup by limit if you want to. And then you can just, it's maximum. I just wrote lim sup just because.
Is it not a constant sequence? Does it really depend on it?
It is a constant sequence. That's the point. The point is that it's a, yes, yes. So this is actually the proof that, yes. Sorry, so I just wrote it that, so if you, okay, you will understand why I'm coming in a minute. So, but the reason I'm coming is that, okay, what is the, so now I'm going to go to multi-terminal information theory. It means there are more than one sender and receiver. So in the multi-terminal settings, you have expressions like this, multilateral expressions, and you want to see whether the equality holds. Okay, that's the singularization. Okay. So I'm going to, so, and unfortunately when you go to multilateral settings, most of the regions, most of the settings are open. We don't know the capacity for most settings, but still I'm going to partition it into two settings. These are the settings where we don't know of good achievability schemes. And in fact, most of the settings are here. That means we don't know a lot of schemes. And here the good questions to ask are what are new achievability ideas, or what are good coding strategies, or if you want to establish rates of convergence. I mean, there are many questions you can ask here. But what I'm looking at this talk and what I've been looking at for the last few years is there are still some settings in multi-user inventory, some very key settings, where we have single letter expressions for which we don't know whether it's optimal or not. So that is my study. The question is, there are single letter schemes and we don't know whether it's optimal or not, and the question is whether they are optimal or not. So the way I'm going to ask this is along the following lines. So when I look, okay, so this was, okay, you can think of this as over time. So initially when I looked at this, there were some schemes here which I showed were here. So that is the first set of results I got, that I showed that some of the schemes for which we don't know optimal, we showed they are strictly suboptimal. So one was with Abbas al-Gamal, and last year we showed for a very important setting in different channel, we showed that that's not optimal. And if you look at all converse theorems in information theory, if you look at it in a particular way, that means from history to until today, oh, this should be a typo, they are really proofs of tensorization, and I can explain that later if you want, but they are really proofs that a certain, just like entropy is subadditive, they are actually proofs that certain other functionals are subadditive. And this might, I can write down certain things which might be surprising if you haven't seen this before, but these are actually proofs of subadditivity. And so once you can test, but subadditivity is something you can test on a computer, and so some of the settings numerically the thing seems tensorized, and that's so I want to understand, what I really want to do is to understand subadditivity and learn from functionals that we know tensorize has subadditivity property, and we can also learn from things that don't tensorize. So my focus of the talk is look at some things that tensorize and try to learn from that or something, I mean, and then see it in new light. The usual subadditivity proofs are either subadditive entropy, or there's a trick by Bob Gallagher where he does identification of auxiliaries and so on. So these are the kind of standard tricks. So that's the setting. So my motivation is to understand when certain functionals tensorize or are subadditive, and how do you prove such things. So anyway, so this is something, this is a joint work with a lot of people. Amin, I worked a lot with Amin Gohari, and he was the person who introduced me to hypercontractivity. And so, I mean, so this is a notion which was it was, I mean, it was there from the late 60s, I think, and the hypercontractivity. So the reason I'm giving definition is because a lot of people in the computer science think of hypercontractivity in the Boolean cube, but here I'm just thinking of arbitrary pairs or animals x and y, and we say that they are, say, PQ hypercontractive. Think of P, these are norms, so these are the moments. If I can bound the x value f of x g of y by P prime, which is the Hilda conjugate, and g of y q. So the I mean, just to make sure that these are like improvements on Hilda's inequality. Hilda's inequality says that expected value of f of x g of y is less than or equal to f of x p prime g of y p. But suppose I can improve this depending on the joint law. The joint law is fixed on mu x y. Suppose I can show that this in fact less than or equal to f of x p prime and g of y q for some q less than p, then my monotonicity of norm, this will imply this. So if this inequality is true, then this is true. That's just monotonicity of norm. So these are inequalities which are strengthening of Hilda's inequality, and you want to know for what p and q does this inequality hold. And so this is an analysis question. So the first person, I think information theory, the first people I think who looked at it was Gach and Alswede, and they related hypercontractivity to set expansion. And this was a largely forgotten piece of work, I think, because, and for the TCS community, I think the work of Kahn, Kalai and Lineal, influence of variables in Boolean functions, that's what brought their attention. So this is not much, it was not mainly used in information theory until it was used first in 76, but then nobody used it. It's been mainly used by computer scientists, also in probability and analysis. So that's the history of hypercontractivity. Reverse hypercontractivity I'll talk about later, maybe I'll do this later. So I will talk about reverse hypercontractivity later, but let me start with this question. So what did Alswede and Gach show? Alswede and Gach showed that so I'm looking at the region of PQs where bigger than 1, so it's some region like this. These are a set of all PQs which are hypercontractive, and they're looking at the ratio Q over P in the limit as P goes to infinity. So they're looking at this ratio, and they showed that the ratio, the limiting ratio, is in fact the ratio of divergences, Kullback-Leibler divergences. And so what am I saying here? So I have so think of a input distribution mu x and a channel w of y given x. Okay, maybe so there's a channel here, there's w as input. So there's an input, say mu of x, so think of, and there's an output mu of y given by channel. Now we know this is a basic data processing inequality. If I input another nu of x and you get an output nu of y, where nu of y is essentially summation over x w of this nu of x, then we know that the divergence between the two output is less than the input. This is data processing for divergences, and it turns out that the best constant you can put here, so you can reduce it from 1, and the best constant here is hypercontractivity. So that's what they showed, that the best constant you can put for any nu, so for any nu x is the hypercontractivity. This is the ratio Q over P as it tends to infinity. And so what we showed was that so this was with Amin here and Venkat and Sudeep Kamath who gave a lecture last week, is that, oh, they are also equal to a bunch of other expressions. So the limiting ratio is also equal. So we know if I have mutual informations, if I have random variable x and y according to some mu, so you can think of, so if I have Markov chain u to x to y, you can think, we know that IU y is less than or equal to IU x. So then we can ask, can we reduce from 1 to some other constant eta? And it turns out that the best constant you can put eta for any u is again is again S star. So these two constants are same. And it turns out that so you can improve the data processing inequality by this constant, which is the hypercontractive parameter. So this is so one small remark which I'm not even typing was that this was claimed to be something else, and that result had a mistake. And I can also write this in a different way. Okay, maybe I'll explain this now. So no, I will explain this later. I'll do the calculation and explain this. Okay, so one of the things I did was to go from infinite to the whole finite case, and so I could show that PQ hypercontractivity is same as any of these expressions. So that's what I could show, that you can see whether they are hypercontractive by just solving any of the equivalent forms. And I will say this in a more general way a bit later. So these were actually extensive ideas in Al-Sweidi and Gach. And so depending on different cases, I have used all of them to get the hypercontractive parameters. So there's no one universally good representation. Depending on which setting you are, I've used this turned out to be useful in many settings. This turned out useful. This has turned out useful. So it's good to know, various things. Now, so in Villani's talk, he talked about Cordero. So it turned out that the analysis people had also found this form a couple of years ago. So this told me last year. So they had discovered this form for functions, but this is the form I'm going to talk about. Actually, I'm going to talk about Braskamp leap type inequalities, which were they considered. So it's a nicer generalization, and you get the whole thing. So what is the Braskamp leap type inequality? A Braskamp leap type inequality is essentially a generalization where I have m functions. So we say that it satisfies the Braskamp leap inequality with parameters lambda 1 to lambda m and c if this holds for all functions. So hypercontractivity is a particular case when you put c equal to 0 and you look at lambda i's. So we want to know which set of all parameters for which its Braskamp leap type inequality holds. And the main thing which I'm going to try to outline today is that all these statements are equivalent. That means to test this is enough to test this is enough to test this. They are all equivalent. Okay. And so what I will try to do now is actually it's very easy to, the proof is simple enough that I can try to show on the board the main ideas. But I hope in the process you will also see some nice, what kind of functions are come up, and the proof has some nice ideas. So maybe it's useful to go at least some of the ideas. So what is the, in the third bullet, there's no x and y. Oh, okay. So nu i's are the marginal xi. So you have a nu on the joint. So and then I have nu I of xi. So it's the marginal of this thing. So I want that the sum of the divergence marginals have the same inequality. Yeah, shorthand notation. Sorry for the shorthand notation. So okay. So how do I prove this? So the proof is not very complicated. So let's assume that how do I show 1 implies 2? So I'm going to show. Really the proof is 1 implies 2. 2 implies 3 and 3 implies 1. That's the way I'm going. So 1 implies 2. That means I'm assuming 1 holds. So nice property of Braskamli inequality is the fact that tensorizes. That means if x1 up to xm satisfies hyperconductivity with parameters lambda 1 to lambda m and c, then if I take independent copies, say n independent copies of the IID copies, xm are n, the IID, they satisfy with the same lambda 1 to lambda m and nc. This is a very simple argument to see why this is true. You just take out products and you just, it's a very simple, it's an exercise, it's a very simple exercise. So I'm going to use this fact. So since I know that this satisfies with lambda I and c, I'm going to assume that NIID copies will satisfy with the same lambdas and nc. So now I want to construct some function that will give me this inequality. So what is the function I'm constructing? So this is the function I'm constructing. So I want to construct, so I'm given a law, I'm given a joint law which is consistent with the, so I am given some auxiliary variable u, I'm given some law which is xm. So what do? I take a sequence un which has the same empirical law as mu u. So this is an empirical law of mu n is, say, mu of u. Okay, so up to integer, you may be off by 1 over n, but I don't care about that. So it's as close to the true thing as possible. And I pick this, so in the space of UNs, it's one point which is, very close to empirical law. And what I do is I look at, so say this is x1n, the sequence x1n. I look at all the jointly typical sequences with this un, and f1 of x1n is the indicator function of this typical set. So typical sets are indicator function of the typical set. So let me call it typical epsilon n of, say, un x1. So that those are exactly my functions. So they are actually just, do you know what typical sets are? I hope you know what typical, Anup, do you know what jointly typical sets are?
I do, but I'm not sure that helps you.
Sign-off, yes. So yes, so essentially concentration. This is all concentration. So what is the so then let's compute norm of fi of xin to the lambda I. So this essentially, so this is what the size of the typical set. So like 2 power minus n iu xi times whole power 1 over lambda I plus lilo of n. That is the norm of this set. Oh, u is, you are given a u. So this is just the probability of the typical set. And what is the expected value of f1 fm of xm? We know that, if everything is typical, then it's going to be 1 in particular. So which means that it's at least as big as 2 power minus n iu x1 to xm. Because everything is typical, then there's going to be 1 times 1 times 1, and the number of typical sets are going to be exactly this. This is just, so if you just plug in on both sides this with nc, you exactly get this form. That's all. So you put a, was that too fast? No, it should be okay. This is just a concentration. So the sets you choose are just the typical images, and once you choose typical images, then you get this. This is a normal, just concentration. So you get this, and you're done. So at least the reason why I chose this as the candidate for FI is really based on a paper by Kerner and Martin, which is the images of a set and the role multi-user communication. So there they had the intuition was there that if you have a message set, it's based on some auxiliary U, and that is the motivation for choosing this particular thing. And I think there is something more to be said, but let me do this. So then you want to go from here to here. So the proof that this implies this is again another proof technique I learned from another of Janusz's papers, and it's really an exercise, and the way you do this is also very simple. So what you do, and this is the standard way of going from. So why can I show that this implies this? You create a path. You actually create a path. So what do I want to show? So I take my u epsilon, u as a function epsilon, as a binary variable. It's 0 with probability 1 minus epsilon, and is 1 with probability epsilon. And the distribution of x1 up to xm condition on u epsilon equal to 0, I take this to be mu minus epsilon times mu there. So this is absolutely condensed by 1 minus epsilon, and x1 u epsilon equal to 1 to be distributed as mu. So you see the weighted average of these is exactly mu. So they are centered around mu, and this is a probability distribution because I assume that mu is absolutely condensed with respect to mu. So when this is 0, this has to be 0. So that's fine. And now you just define f of epsilon to be exactly, the thing. So c plus I u epsilon x1 to xm minus summation I 1 over lambda I u epsilon xi, and we know that f of 0 is 0, and we know that f of epsilon is bigger than or equal to 0. So which means that f prime of 0 must be bigger than or equal to 0, and if you compute f prime of 0, you exactly get this. So this is a trick which I have seen Janusz use in a paper on less noisy with Martin. So that's where I've seen this. It's an easy exercise. So that's the idea. So you create a path, you take a directional derivative or a non-negative function, you get positivity. Now how do you go from this to this? It's again one line, but I don't think I'll explain. Okay, you can ask me if you want to know. It's a one line thing, so it's not much. Okay, so I want to do another characterization starting from here, and I'll tell you why. Because this turns out useful. So what does it mean? I want for every u, I want this sum to be less than or equal to c plus. So I'm going to rewrite in terms of conditional entropies as I'm going to bring all the terms of the u here. I want to say that entropy of xm given u minus condition u is less than this for every u. So these parts don't have u, so I can take the maximum of this. What happens when I take the maximum of this? I get I get the upper concave envelope. What do I mean by that? If you know what an upper concave envelope is, just I take the envelope of the convex hull. So if I function like this, the upper concave envelope is just this function. So that's what I get. So what I need is that the upper concave envelope on the space of distributions evaluated at your particular distribution mu must be less than this value. So there's no u here, so I just have a functional on the distributions, and you want this inequality to hold. So that's the equivalent characterization. So okay, so this is useful. This upper concave envelope, I'll tell you why. So let's go back to, so one of the things of having equivalent characterization is, can I get some new results using these which I could not get before? And I'm going to show you at least some calculations which will explicitly get you hypercontractive parameters, which some of this are useful. So on the first part, I'm just going to work with the infinite Asperi-Gauche So the best data processing constant. So you can call it strong data processing constant. What is the best data processing constant? And I'm going to use this notion first. So let's see how you compute this. Okay, so let's look at this channel. So I have a binary input. So this is x is binary. And I'm going to pass through what is known as noise operator. So it's I'm going to flip bits with this probability. I'm going 1 plus rho over 2 is going to be same. 1 minus rho over 2 is going to be flipped. But x is not uniform. So x has some bias. Let me call this 1 minus s over 2 and 1 plus s over 2. So that's a joint law of x and y that's induced by this. And the question I want to ask is, what is S star? So how do I compute S star? So I look at this functional lambda entropy of x minus entropy of y. So what is that? If I call probability of x equal to 0 to be 1 minus x over 2, so it's lambda entropy of 1 minus x over 2 minus h of 1 minus x rho over 2. So if I plot this function, it will essentially look like, okay, it will look like a function like this. It will be symmetric around the midpoint, everything is symmetric. And then what is the upper concave envelope? The upper concave envelope is just this line joining the two local maximums. And what is the first time that this inequality holds? The first time the inequality holds is exactly when you are at the corner point. That means you just have to solve for, so the correct S star is only set, so d by dx of lambda of h of 1 minus x over 2 minus h of 1 minus x rho over 2 at x equal to s to be equal to 0. So if you can write this explicitly if you want to write this, it's minus lambda over 2 j of 1 minus x over 2 plus rho over 2 j of 1 minus x rho over 2 is equal to 0, or S star would be exactly rho times log 1 plus x rho 1 minus x rho by log 1 plus x 1 minus x. So this is an explicit computation for the hypercontractivity. That's all. So this viewpoint is very useful, because once I know it's symmetric and I know it has only two inflection points, the concave envelope is just this. And what is S star? S star is the first time that the derivative is 0. So what about if I have a z channel? If I have a z channel, how do I compute the best constant? Then it turns out that the graph will look something like it's initially, and then S star is the first time you have the marginal hitting this, you have an explicit formula. So this viewpoint is very useful in terms of concave envelopes, and you can use it to compute. I mean, to guess this is hard, but now you have, even here you get log over log kind of form. There's another example which is very useful. So if I want to compute, so this is using a different representation. So if I want to compute S star between sums of, suppose I have IID random variables, these are IID random variables, say xn, and I have a partial sum xk, where k is less than or equal to n. So we can show that this is less than or equal to k over n. Okay, this is, so it says that if I have a Markov chain that goes through Sn, the sum to Sk, then IU Sk over IU Sn will always be less than or equal to k over n for any IID random variable. So this xi's are IID. So this result actually, this implies, so this is because it's bigger than correlation squared. This result was the result of the fact that rho squared was less than or equal to k over n, was the result of Dembo Amir Dembo, Shep, and so on. But now this gives a very simple proof, and I'll show you the proof is 2 lines. So let me show it for 1 and 2. So what I want is that I want to show that a star of x1 plus x2 comma x1, say the IID, is less than or equal to half. How do I show this? So I have some Markov chain U to x1 plus x2 to x1. So what I'm going to do is I'm going to conditionally independently generate a copy x2, and now I observe that IU x1 plus x2 is equal to IU x1 x2 because of this Markov chain. They go through x1 plus x2 by my construction, but that's equal to IU x1 plus IU x2 given x1, but they are independent, so that's equal to, this is bigger than or equal to IU x1 plus IU x2, but they are symmetric, so everything is symmetric here, so this is equal to 2 IU x1. That's all. That's essentially the proof. There's nothing more than just chain rule to prove this. So, but the way they showed was they went to characteristic function and so on. So you get a very general result from just this. So here I use the mutual information version of it. So this was another result. So you see it at least, and so the finite regime also we have some calculations. So what we showed is that the correlation abound. So Bonavi-Beckner inequality, which is famous in the TCS community, is essentially showing that this correlation abound is tight. So last year when I was in Simons, Jay Kumar and Venkat Guruswamy asked me for the erasure channel. For the erasure channel, that means you have this channel, erasure with probability epsilon, and the uniform. Is this tight? And what we could show earlier, this year, is that it's tight exactly when this condition holds. So the correlation bound is tight if and only if this condition holds. So clearly, if this parameter is less than half, then the hypercontracted region is just this, and if it's bigger than half, it's beyond some point is this, and here we don't know. It's not on the line. So we can show this, and this uses the divergence characterization. So this proof uses divergence characterization. So I've used the third characterization. So you see, you're essentially asking whether this condition holds, and the way you do it is to look at stationary points of this, and when this condition holds, there's only one stationary point, and if it fails, it's not even a local maximum. And this idea of looking at stationary points came from a work of Friedgut, where he applied this to Bonavi-Beckner inequality. So that's how much time do I have? 15 minutes or? Okay. So the last thing I want to talk about today is the reverse Braskamp-Lieb inequalities, because so this is another new result where we prove the reverse from. So here, what is the reverse Braskamp-Lieb inequality? So this was not known before in any form. So we showed the following result. So what is this? So this has some. We know that Helder says that expected value of f of x g of y is less than or equal to f of x p g of y p prime. That's Helder for p bigger than 1. And reverse Helder says that reverse Helder states that expected value of f of x g of y is strictly bigger than or equal to f of x p g of y p prime for p less than 1. 1 over p plus 1 over q is equal to, no, p prime equal to, that's reverse held there. So now what is reverse Braskamp leaf? Is the same thing, or reverse hypercontractivity, you replace this by a larger number q. That's reverse hypercontractivity. So you want to improve the reverse held there. So essentially reverse Braskamp leaf is set of all parameters where this holds, and we want to show that this condition is equivalent to this particular condition. So now note the difference. It looks almost similar, it's not, but it's not quite. So it says that look at all the positive lambda i's. So here lambda i's could be positive or negative, and pick marginals on the positive lambdas. Then what I claim is that there exists a joint distribution considered with the marginals such that this inequality holds. So this is really a max-min problem. It's not a maximization, or it's a max-min problem. So for every set of marginals, there is some joint law. That means there is at least one that has this form. And the proof of this is interesting, because people did try to extend the forward direction in the reverse, and the difficulty was the following. The difficulty was if you had lambda i's that are negative, if lambda I was less than 0, and if indicator function takes 1 and 0, you can't divide by 0, because if I raise f of x to the power lambda I, which is negative, you're taking 1 over 0. So, and this causes issues, and you can't even take limits. This is so what. So the main novelty is how to deal with negative lambdas. So the function defined for negative lambdas is the following. So if lambda, say lambda 1 is negative, then you define f1 of x1n as follows. It's equal to, look at the type of the sequence x1n, that's the empirical distribution of x1n, and look at the total mass that's given. So let me call this type pi. Look at the total mass that's given to the type pi under the mu, and raise it to the power minus 1 over lambda 1. So that is the function I assign. So what do? I take a sequence. I look at the type of sequence. So I look at all the sequences xn says that type is equal to pi, and that's mu of xn that under the product law, and I take this to the power minus 1 over lambda 1. And now if I look at say the lambda 1th norm of x1n, what I get is exactly 2 to the power. So let's do this, it's not hard. So it's summation over all x1n, say mu of x1n, f1 of x1n to the power lambda 1, the whole power 1 over lambda 1, so that's a norm. So what is this? So I can decompose the sum into two things. I can decompose first as sum over types and sum over xn such that the type is equal to pi mu of xn, but this is constant across types. So this whole thing becomes 1. So this is just summation over types. Types is polynomial, so it's like 2 parallel of n. So that's this norm, and if you compute this side, what you see is that what you see there is the fact that so mu of x1n is really like 2 power minus n divergence between the type pi and mu plus lambda of n, and f is going to be f of x1n is only going to be 2 power n over lambda f1 d of pi mu. So when you plug this for the i's that are not in S plus, this term comes from this side. Actually, it comes from this side. So So there exists, so you get a min-max theorem because summing over types, and the types are dominated by a maximal type. That's exactly how you get this. So it's a slightly different piece of argument that gives you this. And the reverse direction is also by concentration. You use concentration to get back that this implies this. So this is a slightly different way of proving than the forward direction. The other thing I want to mention is that there is no mutual information version of this. So if I try to write the auxiliary version of this, you will get divergences. So it's a mix of mutual information and divergences, which is not very, very meaningful. And so I haven't found other ways of doing this. So this is the only way I found of doing this. So that's basically what I wanted to speak today. And I will continue with some applications of hypercontractivity tomorrow and see what else we can have. So if there are questions, I'm